Now, besides damping, which reduces the acceleration or the movement of our structures, and depending on the material, for example, steel structures might have higher damping than reinforced concrete structures. When buildings are exposed to the same earthquake shaking, they respond differently. Let's not make it sophisticated. Let's just concentrate on the same tall, flexible building and the short and stiff building. So Burj Khalifa and White House. The response of these buildings fundamentally is determined based on their strength and capacity, so how strong they are, ductility, which we will discuss it very into details, and one of the most important ones, stiffness. So stiffness is simply the ratio between force and the resultant displacement or moment and the resultant rotation, or in simple terms, mathematical terms, the cross-sectional area of that element, let's call it, the elastic modulus, which represents the material of that element. So any material in the world will have an elastic modulus, or as we call it, the Young's modulus. So steel has one, 2.1 times 10 to the power of 5 GPa, or concrete has one, timber has one, glass has one, fiber carbon has one. Even if you put me in the machine, you can find an elastic modulus of me with the reverse relationship to length. So let's look at it. So the taller or the longer it is, lower stiffness, because L goes higher, stiffness goes lower. The bigger the cross-sectional area is, the cross-sectional area like an I-beam or a rectangular cross-section, the bigger it is, K goes higher, stiffness is higher, and the stronger the material is, so then the elastic modulus is higher, so the stiffness goes higher. So flexible buildings generally deform greatly under stress, and stiff structures deform slightly a little bit lower under stress. So the flexible one will move much more, as you can see, and the short one will move less. One of the reasons of this is stiffness. So the stiffness of the shorter buildings is higher, so it will move less. The stiffness of the taller buildings is lower, so it moves more and is more flexible. Now that stiffness relates to this graph, stress versus strain. And then this stress and strain can be also converted into force or moment, and this strain can be converted to the resultant deformation or rotation. So force and its resultant deformation, as well as moment and its resultant rotation. So stress, just look at the units, is the force over the cross-sectional area, and strain is the change of length over its initial length. Any material in the world, if you put it in an actuator, you pull it or you push it, will give you such a material behavior. Now some will just stop at here, some will continue. The beginning of the curve, as you can see, is a linear behavior. We call this point elastic behavior, and as you can see, the behavior is linear, so the slope of this curve, which can be calculated from stress over strain, like this formulation, the slope of elastic part is called elastic modulus. So we put different materials, steel, concrete, timber, glass, fiber carbon, or me, in an apparatus. We pull me and we push me. I will start making some noises, and then you can see the linear bit of it. The linear bit means that if I release my load, the deformation will go back to its initial position. There won't be any permanent deformation. But any material, after a while, it will move onto a region that we call it nonlinear region, or inelastic or plastic region, which that border is called the yield point. And we use this yield point a lot in designing structures for non-earthquake loadings, if you remember. This nonlinear area is when, if you release the load under any of these bits of the curve, the deformation will not go back to zero. the deformation is permanent and your material or me or the steel specimen will stay as it was. So in normal design of structures, Eurocode 2, which is reinforced concrete, or Eurocode 3, which is steel structures, we just generally deal with linear elastic behavior because we have a specific E allocated for the entire behavior of the structure. This is the easy part, and this is usually what people get taught in their undergrads as a civil engineer. When you become a specialist, when you are becoming an earthquake engineer, we move on to more advanced stuff. That's where stuff gets sophisticated and complex. We move on to nonlinearity because the linear bit is easy to calculate, but if we want our structure to stay in its linear state under earthquake, our structural columns will be 1 meter in 1 meter instead of 10 centimeters in 10 centimeters. That increase of dimension means more material, means more cost to the client, and means less space for us to live in it. So we as earthquake engineers, we know that the material have a nonlinear bit, and we allow our structures to move to the nonlinearity. Also, when moving to the nonlinear bit, we have the ultimate strength, while dealing with the linear bit, we have the yield strength. This yield strength is usually what you have in your normal design. If you remember, you had Fy, F of yield for steel, for example, and then you were dividing it by some values to get a lower value, and we call that the ultimate state design. We'll discuss it in a second. Now, let's quickly have another review of the stress-strain relationship of material. So if I draw the diagram, let's say stress, and let's say strain. If you remember, strain was shown like this, and it was change of length over initial length. And stress was shown like this, and it was force over area. Meaning that if I have, let's say, a bar with a circular cross section, and I apply a force here, the stress will be whatever the area of cross section is, not the area of the entire rod or anything, just the cross section. The force over that area, that will be my stress. And then what can the unit be? So probably kilonewtons, for example, over, if it's in terms of millimeters, millimeter to the power of 2. Or in the honor of the person who named and discovered this relationship, we sometimes call it in terms of pascals as well. For example, megapascals, pascals, gigapascal, and I strongly suggest that you go and check them out on how any of these is related to kilonewtons and millimeters. For example, megapascals is usually Newton millimeter to the power of 2. So everything is nmm because it has an m in the beginning. Or for example, kilopascal is kilonewtons per meter to the power of 2, depending on the situation. Now, when I apply this force, this rod probably will elongate and it will come a little bit down. So it will become here. Now, if this is the change of the length that I have, and this is the initial length that this rod had, then if this is now the total length, change of length will be total length minus L0. So strain will be L minus L0 divided by L0. And then as you can see, L minus L0 is probably in terms of meter or a unit of length. L0 will be in terms of meter or unit of length as well. So this goes with this. So strain is unitless. Now, you can easily see that we can convert these guys to each other. I mean, stress can be easily, by multiplying it by an area, can be force. Or if you remember, there was a relationship between force and moment. So imagine you have a wrench here, and you have a pin or a knot here, and you want to open this. So if you apply a force here with your hand, here, because there is a distance, a perpendicular distance from your force to the knot, there will be a generated moment. So this force goes downward. Because of this distance that you have to the knot, there will be a moment generated. Yeah? Zoop, it moves it. So from this, we could conclude that moment is force times the perpendicular distance of that force. As simple as that. We use this in like real life a lot to calculate lots of stuff. So stress can be converted to force and also can be converted to moment. The same thing happens with strain as well. Whenever I'm presenting it in terms of force or moment, instead of strain, I can say displacement. Because do you accept that this was the displacement, this delta L? So if I multiply this both sides through the initial length that my rod had, it can be displacement. Or as a cause of moment, this can be rotated. So this can be rotation as well. So whenever you saw a diagram of force displacement, moment rotation, or stress strain, they are kind of showing kind of similar relationships that can be converted to each other. Now, imagine this is steel. This curve, which will be the resultant of the stress applied to the cross-section, and the strain, which will be the change of length over initial length, really depends on the material. So the material is the most important thing. Now imagine if it's steel. It will have a curve something similar to this. And this is the point that it breaks. Yeah? Fracture happens. So it gets so long that suddenly it becomes two pieces. On the other side, we discussed that if we look at the initial bit of the curve is usually linear. And from a point, let's say from this point onward, it starts having a nonlinear behavior. So this bit is linear, and this bit is the nonlinear bit. We call the linear bit elastic, and we call the nonlinear bit inelastic, or sometimes plastic. And simply means that whenever you are in the state of linear, imagine I apply force just as much to not reach to this point, which we called it yield point, and I just remove the force. So I reach to this point and then I remove the point, remove the force. It will go back to its initial position. There won't be any permanent deformation in elastic or linear section of any material. But the moment that you pass the yield point, if you remove the force and force goes back to zero, the displacement will not go back to zero. There will be a permanent force and you will see proper deformation in your material or in your rod or in your whatever you're using. Now, in a normal situation, as we discussed, when we want to design any structure, like based on normal codes, we assume that all of our material are acting linearly. All of those calculations are based on this linear bit. And we take this slope, and we call it elastic modulus, and it's simply the slope. So slope of, if you have such a thingy, and then you have such a curve, it's a linear curve, m, if it's the slope, the equation is y over x. So in this case will be y over x, stress over strain. Now for any material in the world, we can put them in the apparatus, we can apply tension or compression, we can compress them or pull them, and we can figure out an E value for it. We have done this for majority of material which are common in construction, like steel, reinforcement bar, timber, cubes of concrete, glass, FRP, carbon fibers, any of these, and we managed to get the E values. You can refer to reference books or just search on the internet and you can find the elastic modulus of material. Just remember that E is just a representative of its linear behavior, and as soon as you enter nonlinearity, as you can see, because the slope is changing every single second, then this does not apply anymore. And in earthquake engineering, we say, okay, I fully understand that you want your material to behave linearly, but because I know that your material, the material that we use, for example steel, have a capability of nonlinearity, why not use that capability to first of all save us money, because I will have sections which are a bit smaller, and on the other side it will give me some flexibility, which we will discuss it later, in terms of ductility and other characteristics, that my building will start dancing with the earthquake, although there will be permanent deformation, but I will save life. So I will give enough time for my residents of that building to jump out of the building, to get out of the building in a safe situation. And then we can reach to fracture or failure. Remember, this yield point, for example, if you check the codes and you say I have a steel of 275, that is actually the strength of this point. So that is Fy. So strength of yield. And what is strength? Strength is the maximum value of stress. We just call it strength. Now, a good example of a material which has such a behavior, for example, is steel. Now, we have material which don't have any nonlinearity, or they're very small in linearity. They can be very strong. So if steel is like this, they can have a graph which is like this. So their strength is higher, but they don't have any nonlinearity. So until the end, all of it is the same elastic modulus. The problem is these guys do not deform and do not give us any warning. So as soon as you reach to the last point, fracture, break, poof, which you don't want to see that. Material like glass or fiber carbon polymers or FRPs, these materials, they just have linear behavior. So no nonlinearity, so it can become a little bit dangerous when dealing with earthquake. But again, there are ways that we can deal with them, and we will discuss it later on. But just remember, they have a brittle behavior instead of a nonlinear plastic behavior. Now imagine the same situation that we just discussed. I have a brittle material and I have a kind of a ductile material. A ductile material, again, it has the linear bit while it has the non-linearity in it as well. But the brittle one is only a linear behavior. Now let's see some examples of this in like real material that we have. So I have a perfect Mars bar here. Yeah, this guy is going to represent the, let's say, the ductile material for me. I'm going to apply some force on it. Imagine this is a simply supported beam or something. I'm going to apply some force to its middle. Yeah. So as you can see, it starts cracking, cracking, cracking. There is crack, crack, crack. Yeah. Yeah, more crack, more crack. I'm just applying, more crack. Now, if I remove the load, trust me, I'm applying load in it. If I remove the load, it will stay like this. So it's now it has passed this yield point, a very low yield point, so I can't demonstrate that. But now there will be permanent deformation. But I have not reached to the end point of fracture. So if I continue and continue, you can see that now I have two pieces. Now I have reached fracture. Now let's consider KitKat as the brittle material. So the same loading regime. I'm applying. I just release the load. What happens? I applied the load, it reached to this point, Because it's linear, when I remove the load, it went back to its initial deformation, meaning no deformation. Now imagine I now apply more load, and you see a sudden collapse. You don't want your structure to be like a Kit Kat because it's a sudden collapse, it's a sudden brittle fracture, and it doesn't give you any warning. You don't want the ceiling on top of your head to fail suddenly. You want it to start making noise, you want it to bend, so you get some information that something bad might happen. So then you check it, you retrofit it, or you leave the house and save your life. A source that you can find elastic modulus of different material as well as their yield point is the Structural Engineering Pocketbook. This is based on Eurocode. You have a free version online as well, so you can check out the resources of this module, and you can check this full book online. Like in one of the pages, yeah, over here. So it has different material, for example, stainless steel 304, stainless steel duplex 2205, cast iron, aluminium, concrete block. You can see for any of those, people have put them in a machine, they have pulled them, pushed them, and they have figured out what is the modulus of elasticity. Pay attention to the units, also the specific weight of them. There is the yield stress as well as the ultimate strength. Yeah, so the ultimate strength is the last point, is the highest point of your stress. That again is a strain. So ultimate tensile strength labeled C, which denotes ultimate compressive stress. Yeah, so the ultimate stress is called strength. Now, the structural analysis generally divides into two concepts depending on whether you're considering the material as linear elastic or you're considering the material behavior as nonlinear inelastic or plastic. And as the name indicates, we have the linear elastic analysis and we have the nonlinear analysis. So the linear elastic analysis is the lateral force method of analysis, for example, the one that you used in the introduction to seismic design, that you design the building based on Eurocode. The only difference was that you apply some lateral loads to your building. Or later on you will see the response spectrum analysis, a method that is based on the structural dynamics of the structure. In case of nonlinear analysis, we move on to more advanced methods. For example, the nonlinear static analysis, or the pushover, or nonlinear dynamic analysis, or the time history analysis. We will discuss these two methods throughout this course thoroughly, but let's read some of the main features of nonlinear analysis. Is that, first of all, is the full time history response of the structure, as you can see. For example, an entire real earthquake, which happened in 1992 in California, a magnitude 7.2, a very high magnitude. We apply it to the actual building and we actually record how the building starts shaking and moving. We have complete material nonlinearity, so we don't stop just at the yield point. We consider the entire behavior of the material. As well as the nonlinearity of material, we have geometric nonlinearity, or the p-delta effect, that we will discuss it throughout this course as well. So we have the geometric nonlinearity considered, we have the material nonlinearity considered. Also, the nonlinear analysis is modified for structures which have base isolators or generally isolation devices which act nonlinearly in structures. You cannot design this based on the linear elastic methods. So the same static gravity method that we always used for designing beams and columns was the linear elastic analysis. In earthquake engineering, we move on to more advanced analysis and we allow our material as well as our geometry to act non-linearly. And we will go through these methods throughout this course. So we are moving from linear all the way to more advanced non-linear. But why is there a big difference? Why we call the linear method not advanced but the non-linear one advanced? The main reason, as I mentioned, it goes back to that elastic curve, or if you remember the formulation of stiffness, F over delta, the force over displacement, m over theta, moment versus rotation, or cross-section times the material divided by the length of the member. This stiffness in a linear behavior building or in a linear behavior structure is always constant. But when we move to nonlinearity, as you can see, the moment that I pass, let's say this is the yield point, the moment that I pass the yield point, the stiffness is not constant anymore. At any second of this curve, at any point of this force displacement relationship, you can see a different stiffness. So in the previous softwares, the stiffness is always constant, so the calculation is with a set stiffness, while when we move on to nonlinear structures, that matrix of stiffness is changing every single second depending on how much force is applied. Why our force differs? Because the force is related to acceleration. Now the acceleration is changing every single second, as you can see. Goes up and down, up and down. As this up and down and up and down goes, the force changes and changes and changes. As the force changes, the stiffness changes, the stiffness changes, the stiffness changes. So it gets harder and harder for the analysis to calculate and for us to analyze our buildings. As we carry on, I'm sure you have noticed that the lecture slides are full of and rich of text. We're not going to read every single sentence of it. It's your duty to read these because we use these slides as lecture notes, so they have lots of points, but when we're talking about them, we're just talking about the entire concept of it. So please, after listening to this lecture, go through the text as well and make sure that you understand every single second of it.